Hey everybody, this is Brad Dyke reaching out to you and saying hi. Going around the next round of 1, 2, 3s with discussion, and I thought, I had some ideas and I'm getting some questions. And I thought, well, let's combine them. First part is let's talk about your stuff, right? Now, what I mean by your stuff is that over time, as you're testing, growing, learning, inheriting, getting free stuff, whatever you want to call it, you have the same problem I have, and that is once you got a whole bunch of these, what can you do when you've already moved on to your next project? Well, the key detail about that is to understand the nature of that question. Our IT labs that we have built out in our personal homes so that we can experiment and learn how to do things really cool and stuff, as valuable as it is, eventually we get to the point of, well, technically speaking, we can't bring them together. Now, that's for a different video, by the way. I'm going to ask that question to the general community. But, when you've got those resources and you got older gear and you got newer gear, you have to ask yourself the question that when you look at it, and may it be, hard drives, CPUs, additional add-on I/O, and just a variety of different systems and components and so on. And you've got the hardware environments that what you're working with, and you have older gear that's out here that you want to repurpose, refunctionalize, or, just basically continue to play. And, when you're working with this kind of environment and you get all this gear working, then you're kind of stuck because you're like, well, how can I use this gear? Now, the use of the gear is basically driven on the principle of you've learned something, and you've got this hardware, it's laying around the house, and I've already done a couple of videos about expanding the role of your home as part of your IT environment. Learn how to do what we call operational hardware deployments to, maintain your lighting schedule for the day, to always make it look like you're here so nobody tries to rob you, that kind of stuff. But the other side of the fence is, what can we do once we've done what we've done with this gear? Well, you can sell it. Obviously, that's one option. Or what you could do is look at doing what's called a combination. Now, a combination is basically where you're taking older and newer gear and you're trying to put it into a single platform environment. And this is where it gets a little dicey, but it's actually doable in the old school, if you want to put it that way. That's probably an accurate way to say it, such as Beowulf, where all you need is what we call an entity with an assigned value numerical-wise, and it then joins into whatever you're doing, and it will add its compute functionality to it, maybe small or big. Now, unfortunately, we don't do Beowulf anymore. Not really. We look at what's called compute value. In other words, we want to throw firepower at databases, or we want to throw firepower at cryptocurrency, or we want to throw firepower at X, Y, or Z. Not necessarily a supercalculator, which is not what you want. And I agree. We don't want that. But what could be doable? And that would be what we would call the next step beyond what we have today. That is single entities. May they be the Pis, may they be micro machines, may they be full-blown servers, but in my opinion, all of it together. Yep, you got it. Little and big coming together into a pool. Now, this is something that I put the challenge out there to our IT coding software and open source specialists out there. In other words, the guys and gals who are writing the software code in Linux and other environments to kind of fully begin to take advantage of what hardware can do. Now, what do I mean by that? Well, the hardware industry has always been ahead of the software industry. They're always trying to stay what they call the core bandwidth of the environment. And software has rarely ever been the core bandwidth of anything. Why? Because, number one, as you build new hardware out, you got to learn it. And you got to know its idiosyncrasies. You got to know its allocations. You need to know how it works in DMA environments, and so on and so on and so on. And DMA, by the way, is direct memory addressing. So what you're doing is when you bring a piece of hardware to the table, and that hardware, because it followed some protocols, and I've done videos on that too. It's the protocol is the secret sauce. So that's basically hardware's coding in here that carries a USB protocol in this particular case, a USB 3.1A output card. And because of that, then I could go in and start writing software to maximize its effect. Well, the truth of the matter is that doesn't change much when it comes to what we call static processors. Static processors. Let me explain that. Let me show you here real quick. Now, what we call a classical CPU. Now, this is a big machine, right? Big internalized world, if you want to call it that. It is actually a static processor. What do I mean by that? Well, basically written inside this chip is a series of instructions and algorithms for it to do its job. Now, the key thing about that, hang on a second, I need a sip. The key thing about that is because it's a uniformal construct, in other words, it's completely designed and structured, its pathways are very efficient and very fast. But what if you were dealing with GPUs? Now, GPFS, sorry, wrong terminology. The value of a GPU, or the central processing graphical processor on this guy, which resides smack right here in the middle, is basically not a static processor. What it is an attribute processor that has the ability to do executional value instructions, but has a void in the middle that says, please give me my instructions and I'll calculate, and then I'll do the next set of instructions and I'll calculate, and so on. Now, the key detail about this guy is he's structured and everything is known about it. So therefore, CPUs, central processing units, use these type of processors for your motherboard. GPUs, NTUs, STUs, that's storage processing, basic processors like an i960 platform and so on. These processors do specialize, or they have open architectural CPU processes. They can be very dynamic. That's the key word. They are very flexible, and they have a lot of scalability, and they have some functionality to them. But unlike an NTU, or a network processing unit, the processes of NTU processing for the MPU on a network card is very defined, but is flexible. It's not like a processor. It has some onboard resources it can use that can step away from the processor and offload. And that was the principal idea about GPUs. How do we get the processor from stopping and having to deal with all this extra overhead? But it's got to be super flexible. So for network protocols, they didn't have to really go the route of something like a GPU. They could actually have a slightly more flexible style processing for handling network traffic, and then the MPU could offload what we call network stacks into the network card away from the processor, and that's called deferring CPU functionality. And that's perfect. That's really great. Now, here's the challenge. All of you software coders out there who have been writing stuff kind of like ProxMox, what is the biggest headache about clustering? Well, one, it's difficult to set up. It really is. Because most software coders think as coders. They don't think as that new kid on the block who's got 4 or 5 Raspberry Pis, can run in a GPU environment, has the basics, and that's it. So going in and doing advanced CLI configurations and doing advanced protocol integrations, advanced, SSH, secure style connectivity, it's complicated. But I would say ProxMox is probably the closest one out there that actually is starting to head in the right direction. Unlike TrueNAS or FreeNAS, if you're still using FreeNAS, and other versions, they principally rely on a platform that has a certain amount of cores, RAM, and so on. ProxMox doesn't care about that. ProxMox can actually have a series of different nodes out there, or different machines, and they throw their cores into the equation, and you can basically balance them out as you do that, so you can accomplish your goal. What is the goal? Well, The principal goal is that you want to make sure that every single available processor you have out there could be put into a clustered pool. And what could that pool do? Think about it for a minute. The most important thing is what it can do is it creates a pool of RAM and CPU. The secondary thing it can do is it can do services. Services like print services, okay? Security monitoring. It can do storage services. It can do all of the normal ProxMox or other VM entity environments, domain controllers, the works. It can do all of that, but it can also do more. You can also create what's called a scalable for an AI. Now, caution. AI in this industry that I work in is not the Terminator AI environment. But, for clarification, just like anything else in the industry, it can be used in a detrimental way. It's about morals and values. You can design anything to do anything, from viruses to malicious software to impersonating, an attribute or an account or an individual, and so on and so on and so on and so on. There is no real justification for this except for somebody trying to get ahead of somebody else. So I want to say that moralistically out there before I go forward. So as I go into this discussion, we need a new type of clustered operating open source based GUI driven web environment per se. I'd call it more of a web GUI that requires very little on the CLI side to set the instance up and allows for a fairly easy 1, 2, 3 process like ProxMox has done when you build its clusters out. It's actually pretty straightforward. And it needs to scale across all processors. Now, the challenge of that is that there are a hell of a lot of processors out there. That's the problem. Usually they'll run with Linux baseline codes and get most of what we call the past 10, 15 years of processors. But no, not really. Because the reality of the fact is the original processors, even if they're Pentiums, x86 is still the core. RISCs are augmented x86 instruction processors. And so it's really not that hard to go back and say, oh, well, if somebody's got a Pi card, an Intel Pi card, and it's got a core processor on that card, or you have what's called an independent bus board, which has a small little PCIe CPU controller card, and it's got a bunch of GPUs on it, and it's the GPUs that do all the work, and that little CPU, which is probably something like a Celeron, is just doing the workloads. Now, to be able to bring all of that gear in, put it into an instance engine, and parse it out for deployment. Now, the other trick about doing it this way is when this is done, you've got to seriously think about the allocations. Now, yes, since I've been using ProxMox as an example, let's stick with that. RAM and local disk storage isn't that greatly manageable. The reason why is because of the nature of the types of devices we're putting into the equation. The functional control over those resources isn't very broad for a basic PC box like that Dell 4000 series mini PC. Pis, for example, Raspberry Pis is another example. We go down dumb and we go big. So I think the added value for doing a new type of clustering that can support any service environment goes all the way back to 1999, about 2002, when we used to have these VMs that existed, and they weren't VMs like we call them today. They were basically virtual machine services. Basically, they were just resources and a service, and it ran. VMware came in, kind of flipped it on its head and restructured it, and VMware became the precedence. But now, today, we're kind of going back to the original nature of VM, and that is with Docker containerization, we're doing it again. So that's a great lesson. It's the same lesson we had to learn when a vendor company came in and pitched the nature of what we call storage into something and took us down a road. I know this because I spent a big piece of my career dealing with EMC. It was the company. And EMC managed to kind of control the market and force the storage to go this really weird pathway. But over time, I would say probably, and they saw the writing on the wall, by the way, they knew that their trick was going to fail soon. And what I mean by that is when EMC came on board, they re-hyped the nature of storage. They said, oh, yeah, you can have a single disk in this drive and it could die. But if we put two disks together and we put this confounded device behind it called what's called a failover bus, we could have, two drives functioning, and we could times that by 10. Now, what they were saying is what Teradata had already done. And they were so seriously worried about that, they went out and they basically bought them. You see, the strategy was that we want to reinvent the terminology of storage so that we can charge the heck out of people. It's in a nutshell. Ridiculous charging. Really seriously. I mean, the United States Armed Forces, they bid into it. They bought it. They, I built it. I like, wow, this is not really needed. But yeah, we can do it. It's a requirement. We built those environments. They were huge, giant machine environments. And then over time, and this is a credit to all of you IT vets in the past, I'd say 10 years, you began to figure it out, what EMC was doing. Now, EMC even realized they were being discovered, that they were basically price hiking the disk storage industry. And that caused a big downpour effect of how much money it was required to get what you need to get done. Because the rest of the industries were able to finally kick EMC out of the equation and say, you don't have to do it this way. You can do it better and cheaper. They were spot on. They really were. They knew the truth. Those veterans out there also knew the truth. I knew that truth. I was spent a quarter of my career decommissioning EMC storage arrays to put them on more realistic platforms that were easier to support. So with that being said, in time, from CPUs to RAM to storage disks and so on, we're now in the era of look at all this surplus out there. And you're the people out there getting this gear in your hands. And wouldn't it really be cool is if you could just put these guys in, they would power themselves up. That would be the optimal cluster, by the way. Your nodes would power down in a very, very low power state until they're needed. Hence, your vendor hardware is going to last longer that way. The beauty of that wonderful strategy is that we have a cluster that provides compute and resourcing, and that's it. It's not for databases. It's not for that. It's not for this. It's not for whatever. No, it's not. It is strictly a cluster of resources, which means all your older hardware gear, as you need more compute power, at least for today, even if we could build this software now, we would power more resources on, bring them online, and then we could scale the compute power down, and then you power it all back down. That would be excellent. So, with that being said, my, again, statement to everyone out there in the industry of open source OS / clustering development, think about that idea. We need it. We really do. I mean, it's the next logical step that we need to take. There is no ownership of such a thought. You can't take possession of that, claim it as your own, because obviously when you work with ProxMox, very quickly you start to see the failings of ProxMox, which are very similar to the failings of VMware. AWS has done some of that the right way, but unfortunately, AWS is in the same mindset as Dell and EMC, and that is they maneuver to try to possess the industry and drive the pricing point on that. But the other side of the fence for AWS, which is different than EMC and Dell, is that they didn't try to own it like EMC did for 10 plus years. That's significant. Just out of curiosity, if you're wondering about that strategy, I think EMC racked in a slick 1.5 billion in profits on that. That could have been $1.5 billion put into more development of our environment. Instead, it just went into the pockets of people who knew how to scam us by using antiquated environments and terminology and buzzwords, and you're working on a storage array that's actually technically 20 years old. That was back in the day of the mainframes, and it's a trick. So I am extremely cautious about those kind of things in the industry, and I steer my customers and my company that I work with in the right direction so that we can stay as open source as possible, and or vendor source requirements as necessary, because professional services are that. They're professional services and you need them. But can you imagine what the effect would be is if you brought all that together into an open source ProxMoxy kind of footprint? Same way with with TrueNAS, they kind of have the simple setup. pfSense is the same way, a very simple setup to get things started. Then you jump into the web GUI, and then you can rock and roll, and so on and so on. And I think the strategy for clustering is the detail that's missing for now, because it's still pretty core when it comes to specifics. So then you get into some advanced CLI, and I said, no, you don't need to do that. We just need those new additional resources brought into that equation. And then that's the model we want to go with, because now all I have to do is go to my IP pool, create a virtual service. That's the right word, virtual service. The service does whatever. Print server, proxy set, ClamAV, daemon, whatever. And it's out there doing its job. And I'm using Raspberry Pis, I'm using Avons, I'm using Intel Bridgers, I'm using PC-based motherboards, server motherboards, and so on, with a very robust network switch. And with that being said, keep it simple, stupid. Make it easy. ProxMox, I give you a thumbs up for that, because you do. That's the right approach. Don't try to make a new industry and try to create new professionals. All you're doing is price gouging and trying to control a market that should not be controlled at this time in our lives. Why do I say that? Because we know the effects of lying to ourselves and trying to reinvent things so that you appear to be the expert because you've called it a different name. It's still the same thing. If you want to know what I mean as an example, okay, cool. Those of us who are storage experts, as in way back to the days of AMDALs, mainframes, and so on, and they know what SCSI is and all of that, the reality of the fact is storage is truly just storage. Now, I get it that, all of these experts out here who know this, how do I find my niche? How do I show myself as an expert? Okay, I can cheat. I can rewrite some software, use the back-end protocols that obviously do exist, such as HBA interface, DFM, so on and so on and so on. And, but that doesn't matter because I'm going to throw a big name in front of it. It's called ZFS. Now, I remember ZFS when it was a piece of hardware, not a piece of software. That goes back quite a few years. And it was actually a pretty awesome motherboard, to be honest with you. It was a Sun Microsystems kind of footprint when it had a gig of RAM on it. I'm sorry, 1 terabyte of RAM on it. The only problem is the hardware hadn't evolved effectively to be able to parse out that 1 terabyte of RAM effectively as what we call tier caching. But the principles were all there, and the industry was trying just to reinvent the terminology of what we would call redundant array of inexpensive disks, and that would be called RAID. They want to call it other things. They do that because then they become the expert by putting another layer of terms in front of the true nature of these environments. RAID 1, RAID 0, RAID 50, RAID 5, RAID 6, so on and so on. Or RAID 0, which today we call HBA mode. In other words, every disk is by itself, and you let a piece of software kind of control everything, which is also not the greatest deal in the world. I particularly like hardware RAID. Whether a monocle amount of communication leads to the operating environment, leave it alone. It rocks and rolls and takes care of itself. It will expire disks. You swap out the disk, you put the new one in. There's zero impact on the environment. Focus on your code. Focus on your tools. Focus on your services. Don't focus so much on software storage solutions. Too much. TrueNAS is a pretty cool platform, and the reason why it gets my endorsement, by the way, is because it can do RAID in the clear. That's fine with me. I can also throw out single disks, just standard SATA disks, not HBAs. That's the trick, by the way. Basically, in a nutshell, I can do both. I can do HBAs. I can do paired SATA disks on SATA controllers. I can do RAID controllers. I can do anything. So, and that's why I give it a big thumbs up. Some of the others are, they give you headaches. But the point is, can you imagine what it would take if you brought all of those capacities, the protocols, put them into that master cluster resource environment, CRE. That's what I'd call it. Cluster Resources Environment. CRE represents the whole kit and caboodle. You've got 490 gigs of RAM. You've got 110 processors. You've got 15 terabytes of disk storage distributed. You can parse the storage, or you can make it just one big blob with with some overhead damage in I/O, but it would work. And all in all, in general, that would be really cool. That would really eliminate the requirements of operating environments to be really much of anything, except for your local PC. I'll talk to that in a different video, because I do genuinely have to say that with that comes a good operating environment for your requirements. So I'll talk to that in the next video. But think about it, guys. And gals, it's just a thought, right? It doesn't exist today. If you've got the gumption, I'm too old for it. But if you want me to test it, cool, I will. I'll have no problem with that. But hey, just giving ideas out into the void of IT and people wanting to learn more stuff, to do more stuff, to see if this is something of value. Well, this is Brad Deck signing off. God bless you, and you guys take care. Bye-bye.